One of the few considerations that is directly in the control of the researcher that's going to impact the precision of estimation or the width of confidence intervals is the sample size that is taken. So the number of observations that are collected either in an experiment, from observational data, in a survey, whatever the case may be, the number of observations is something that the researcher can actually decide upon. And by choosing a correct or the correct sample size, the researcher can guarantee that they have enough precision within their estimation procedure in order to make the conclusions that they're hoping to make. And so it's one of the factors that's going to influence the results that's actually within their control. As a result, it's quite important to choose the correct sample size. And so the use of confidence intervals to choose sample sizes is actually one of the techniques that could be employed by researchers. And so the idea is that the confidence intervals themselves can be used to determine how large of a sample is actually required in order to achieve their desired outcomes. First, we can think about this through the width of a confidence interval. And so if we consider the normal-based confidence interval for the mean, that's going to be given by x bar plus or minus the critical value times by the standard deviation, the population standard deviation, over the square root of n. A similar procedure is going to apply to any confidence interval that looks like this. And so, for instance, if we're thinking about proportions, we can use a very similar procedure for the proportions. The idea is that the sample size in this situation is going to impact the width of the confidence interval, right? So the width of our confidence interval is given by 2 times the magnitude of our critical value times by the standard deviation over the square root of n. And in particular, the thing to note here is that the square root of n is part of the factor that influences it. Right? And so by choosing what n is going to actually be, there's sort of an influence on the whole width as a whole, right? And so this is the way that we're going to be able to make use of confidence intervals in order to recommend sample sizes for a given survey. Now, in the term that we add within our confidence interval, this z alpha over 2 times by sigma over the square root of n, this is given a name. It's called the margin of error. And the margin of error is defined to be half the width of our confidence interval, right? And so if we take the width to be 2 times this expression over here, then the margin of error is 1/2 of that, and so we can just cancel out that 2, and we're left with just the magnitude of the critical value times sigma over the square root of n. This is given by the margin of error, and so another way to think about the confidence interval is that we take x bar plus or minus the margin of error. Right? And so that's why we actually refer to it as the margin of error. It's because when we're reporting the confidence interval, it becomes the thing that we add or subtract to. It's the margin that we have in terms of our error in estimation. Okay, so the margin of error is actually expressing the uncertainty that we're reporting within this estimation. Right? Now, we can end up selecting a sample size based on the margin of error. So if a researcher specifies a desired margin of error at some set level of confidence, then the sample size can be changed to accommodate this. Right? So for any fixed alpha, if we fix our confidence level, then z alpha over 2 is a constant. The population variance is not within the researcher's control. That's some fixed constant that we don't have access to. Right? And so in the margin of error, the only other piece of it that actually is sort of within the researcher's control is the sample size, right? Because we have that the margin of error is given by z of alpha over 2, the magnitude of this, times sigma over the square root of n. And if we're saying that we can't change z alpha over 2 and we can't change sigma, then all that's left is being able to change n, right? And so in this way, we can sort of control the width or the margin of error just through the sample size itself. Okay, and so if we have some level that we want the margin of error to be controlled at, right? So let's suppose that we don't want the margin of error to be any larger than m, right? Whatever m is, depending on the context, right? You could take m to be 1, maybe you take m to be 0.5, maybe you take m to be 100, right? It's going to depend on the situation. But we say we want the margin of error to be within some set value. Then what we can say is, well, the margin of error is given by this expression, z alpha over 2 times sigma over root n. So we want that to be less than m. And if we rearrange this expression and we solve for n here, then by solving for n, the way this is going to work is this is ultimately going to tell us that z alpha over 2 times sigma over m squared has to be less than or equal to n, right? And so what this is going to give us is it's going to give us a lower bound on the required sample size in order to draw the conclusions that we actually would like to draw. So a few important points. First, we need to round up this number, right? Sample size can only ever be an integer, and so this actually needs to be rounded up. And the sort of utility of this comes from the researcher actually being able to specify the margin of error that they want, right? So what this is going to allow them to do is to be certain at some set level of confidence that the overall confidence interval is going to have a specified width, right? And so if they say, I want to be 95% confidence that my confidence interval is only going to be of width 2, then they can choose what sample size they're going to need to do this. Of course, to actually apply this technique in practice, we need sigma, right? So we need sigma, we need alpha, and we need m, okay? And so this is only going to apply if they actually know what sigma is, but if they have the capacity to know that information or to get close to knowing that information, then this technique can be applied. Okay, and so the population variance is going to be required as well. Right? So in this context, what this is telling us is that if you are willing to specify all of these things before you've even run your study, you can plan your study around knowing the sample size. Okay? So let's take a look at an example to make this all clear. So we have a team of biologists studying the effects of a new fertilizer on the growth rate of tomato plants. They want to estimate the average increase in height of tomato plants after 2 weeks of using the fertilizer. Now they know from previous studies that the standard deviation in plant heights is going to be 2 centimeters. So this is known to be what sigma is, and that the growth rate is roughly normally distributed. They want to be 95% confident that the true mean falls into an interval that is 1 centimeter long. Right? And so what they're saying here, right, is that they want the width of this confidence interval, right, to be equal to 1 centimeter. And so that's the same thing as them saying that they want a margin of error to be equal to 0.5, right, 1 over 2, because the margin of error is half the width. And so they essentially want to be able to come up with a confidence interval that's going to be x bar plus or minus 1/2. Right? And the reason that they want this is likely due to whatever the context that they're working in here, right? Perhaps being within 1/2 isn't going to change the conclusions that they're actually going to draw, right? Maybe it doesn't change the ultimate decisions that they make with this. But so what we know here, right, is that sigma is 2. They want alpha to be 1 minus 0.95, so that's 0.05, right? And they want m, in the terminology from the previous slide, to be equal to 0.5. Okay? And so then taking all of this information, we can plug that into the formula and determine what the required sample size is actually going to be here. Okay? So because it's normally distributed, we can continue with the interval, the normal-based confidence interval. So alpha is 0.05, Z alpha over 2 is the Z alpha for 0.025, right? We can get this value using R, using the Q norm function in R. So you always plug in the alpha value into Q norm, right? Alpha over 2 is 0.025. So we plug that in and we find that that's going to be negative 1.96, right? Using negative 1.96 for this, we can also use sigma equals 2, and the overall width is 1, so the margin of error is going to be 0.5. Right? So this is all of the given information here. If we take that given information, then the necessary sample size is going to be given by the critical value 1.96 times 2 over 0.5, all squared. That gives us 61.4656. And so then what we're saying here is that we need to take a sample size of at least 62. Right? So we need 62 people in this study at least, or 62 tomato plants in this study at least. And if there's at least 62 tomato plants, then we can guarantee that the margin of error is going to be less than or equal to 1/2. Right? An important reminder here, we should always be rounding up the sample size because we can't survey 61.5 tomato plants, and so instead we have to take 62. So this is the general procedure with using this for sample sizing. So the important piece is that the researcher is actually able to specify the margin of error that they want, right? And again, the way to be thinking about that is that they can then think about this as they want x bar plus or minus some fixed constant, right? And we've been using m as that constant, so we'll write this. They want this to be the interval, and all they have to do is decide on what m is, and then from there, we can work out what does the sample size actually need to be. A similar procedure is going to apply for proportions, and that's because proportions are based on the same underlying confidence interval. right? So if n is large enough, then we can use the normal-based confidence intervals for the proportions, and so then the same procedure can be used to find sample sizes, right? So the confidence interval is going to be p hat plus or minus z alpha over 2 times by the standard error in this situation, right? So if an estimate of p exists, then we can use this for the margin of error. Specifically, we can take z alpha over 2 times by p hat times 1 minus p hat over the square root of n, and that will work as our margin of error. Alternatively, we can actually just take p equals 0.5, and taking p equals 0.5 in this expression right here is going to give us the most conservative approach. So it's going to require us to take even more individuals than we might otherwise require, but that's going to guarantee that we get a large enough sample size here. So if we want to find the margin of error less than or equal to m, then what we're going to find is that rearranging the same equation here, we are going to get that z alpha over 2, the magnitude of that has to be less than or equal to m here, right? And then we'll find that if you rearrange this whole equation here, we end up finding that n has to be greater than or equal to z alpha over 2 over m squared times by p hat times 1 minus p hat, okay? And if we think about plugging in 0.5, you can plug in 0.5 there, right? So use p hat equals 0.5 to be conservative when no weather estimate exists. Otherwise, the procedure is much the same. So we can take a look at an example just to make sure that that actually makes sense. So researchers are interested in understanding the proportion of birds of a particular species that migrate in any given year. Now, they don't have historical data, but they wish to have a 99% confidence interval that has a margin of error of 3% or less. So what we're saying here is that they don't actually know what p hat is likely to be, right? They don't actually know, in this case, what is p hat. And so they want to plan a study so that they can end up having p hat plus or minus 0.03, right? They want a margin of error of 0.03 or less, and so they want to get within 3%, right? And so again, in the context of the problem, 3% maybe is a significant value for them. If they can get within 3% of the actual value, then they can act in sort of the same way no matter what. But all of this is to say that because we don't actually know what p hat is, then we want to be as conservative as we can be in this case, right? And so what we're going to say is that the margin of error is going to be z alpha over 2 times by, in this case, the square root of, and then we use 0.5 instead of p hat, right? So 0.5, 1 minus 0.5 divided by n. So this is what our margin of error is actually going to be. And so if we want to solve this 0.03 equal to this value, and then we can work out what's actually going to happen here, right? So we can start trying to pull through the information here, right? So we need to be based on p hat equals 0.5. The alpha in this case, because we want a 99% confidence interval, is 1 minus 0.99, so 0.01. So z alpha over 2 is 2.58, right? We can get this using the Q norm function in R, where again, alpha over 2 here is going to be 0.005, right? M, in this case, the margin of error is going to be equal to 0.03. It's 3% in this case, okay? And so we need n to be greater than or equal to our critical value over the margin of error squared times by 0.5 squared. If we plug in all of the values for this, we find that n has to be at least 1,849. So in order to get a confidence interval that they're 99% confident is within plus or minus 3% of the truth, then they require at least 1,849 samples in order to do this, right? So 1,849 birds would need to be tagged and then observed. This procedure works fairly well. However, we should take into account some additional considerations for it. So the first is that there are going to be other techniques that might be useful for sample size calculations, right? And so, for instance, there are going to be techniques based on what we would call the power. There are sort of other considerations that are going to come into play here. Sometimes your sample size is constrained based on access to resources or the number of observations that are even possible, right? So this is just one approach to doing it, but it's useful to start thinking through when you're planning a study, how do we want to choose our sample size, right? Because making sure that you have enough data to actually draw the conclusions that you want to draw is going to be a lot better to do when you're planning a study versus when you're trying to analyze that study, right? So it's a very important consideration. There's a whole bunch of techniques. The margin of error technique is just one of the possibilities here. So it becomes absolutely crucial when you're planning studies. Now, one of the things is that in order to apply the margin of error technique, there must be some estimate or knowledge of what the population variance actually is. This might come from past knowledge. It might come from a pilot study. So maybe you run a small scale experiment, you estimate what the variance actually is, and then you use that value. In this case, if you don't have that information, then you're not going to be able to use this as a method of sample sizing here. Right? It's also only going to hold for normal-based intervals, right? So we're using the Z critical values. We're taking from the margin of error from a normal-based interval for the mean. And so that's really the only way that this specific technique is going to hold for. However, we could apply similar procedures based on t-based intervals. However, the problem that we run into with doing this is that if we need the critical value from the t-distribution, the critical value from the t-distribution depends on having n-1 degrees of freedom, where n is the sample size. And so in this case, the margin of error is also going to depend on the sample size through the critical value, as well as through the actual sample size itself, right? So in that case, we're going to be looking at, say, t n-1 alpha over 2 times by s over the square root of n. Right, and so here we have an n that shows up in the square root of n. We also have an n that shows up in this critical value here. And so if you take different values for n, then you're going to need to be changing both of these things, and it becomes a lot more complex computationally to do. Really, at that point, we're going to need to use a computer to solve these things, so you can't really do it by hand, right? So this is going to become a more computationally challenging problem, and it's not normally going to make a big difference. If you just assumed that you were using the normal values, you're normally going to get roughly the same procedure instead. And so one of the things is, if you perform the normal-based procedure when it's not appropriate, and it recommends a small n, so you take the procedure and it gives you something like n is less than 30, then you might want to consider other techniques for sample sizing, right? Because at that point, perhaps this is a bad approximation, but if it recommends that you take 1,000 observations, it's not going to make a big difference whether you use the t-based procedure or the z-based procedure. And so you may as well stick to the one that's a little bit more straightforward to do. Okay. So the other thing to note is that often this is going to be just sort of a rough approximation, right? Because the variance is almost certainly actually unknown, and so it's an estimate there, right? And so this is sort of a ballpark figure. You should take this as sort of an estimated starting point and sort of get you into the range of the amount of samples that you would need, even if it's not going to be sort of exactly perfect, right? It's going to get you sort of an idea. Do you need 100? Do you need 1,000? Do you need 10,000 observations? So by using the theory from confidence intervals, and specifically by taking a look at the margin of error that arises from confidence intervals, we're able to determine the required sample sizes based on those margins of error. And the idea is that we can set what our sample size or what our margin of error should be. We can set what our level of confidence should be. And then as long as we have some way of understanding what the population variance is, then we can plug all of that in and find out what sample size is required to achieve that margin of error. The same procedure applies whether we're dealing with proportions or with means. And while there are sort of more complex ways of dealing with sort of the non-normal based mean procedures, the normal based ones are going to give us a rough enough approximation to actually use in practice. In practice, there might be other ways that we want to try to do the sample sizing itself, but sample sizing is going to be a critical part of doing any type of study design, and the margin of error technique is one useful way of doing that.